Good afternoon, ladies and gentlemen. I would like to present you some lessons we learned about hydrogen technology, and particularly in view of the conversion to a carbon neutral society. So first of all, it's very important that we address climate change. This is the most extreme menace we have today. We have extreme weather events. They get stronger and stronger, and they go up to unprecedented levels. We see that in Turkey, for instance, we had 70 dead at the Black Sea. In Germany, Belgium, we had 120 dead. And in China, we had 300 dead just on flooding. And these were big floods, but floods which come over and over again now, and which are come in line with the climate change. So we also have wildfires all over the world. So we have to pay a lot for rebuilding the damage beyond the loss of lives. So only in Germany, we had about 13 billion euros assigned for rebuilding and support of what happened here in 2 days. And I would like to take this number later to compare what we have as expenditure we foresee for changing the energy infrastructure. So what is the long-term prospect? And the IPCC came up with 3 resulting global warming scenarios which are above the goals, and with 2 which are within the goals. These here for 1.8 and 1.4 centigrades are within the goals. And these clearly show that from about 2075, 80 on, we have to go to negative emissions. And the same from about 2060 on for the 1.4 centigrade goal. And all the others run out of control, basically. They will deliver a global warming which is beyond our control. What are the culprits? The culprits are carbon dioxide and, to a very high degree, methane. So methane has multiple sources. It's not just energy, it's also agriculture, but to a certain degree and to an increasing degree, as we know now, it is energy. All of this is still covered by sulfur dioxide emissions, which contribute to a negative, here is 0, a negative global effect in temperature. And therefore, if these are cut out, and they will be cut out once we stop burning coal and oil, the whole thing will get even worse. But there is no chance to cut the big things out without cutting out the SO2. So what do we have to do? We need at least a net 0 CO2 emissions. And secondly, we need strong and rapid sustained reductions in CH4 emissions, it's methane. These are quotes from the IPCC, these are not my sentences. And therefore, the trends of global surface temperature will begin to emerge from the net variability without 20 years. So we feel that 20 years later, we won't feel it any earlier. What does it technically mean? Carbon air capture will be very important. It will gain impetus. And natural gas use and potentially synthetic natural gas have to be evaluated for the methane slip. In other words, there is little room for these gases to really step in a carbon neutral society, or let's say in a climate neutral society. So hydrogen will be a suitable substitute for natural gas and fossil fuels. This is a hypothesis I make here, and I will show you later on that it is pretty likely. Hydrogen is a precursor also for ammonia, for methanol, for synthetic naphtha, which is used in the industry, and for the chemical industry and synfuels. We have unavoidable CO2 process emissions, and these can be tapped as CO2 sources. So we need carbon sequestration at the big CO2 emitters, which is, for instance, cement production. And if these switches to these modern energy carriers are done appropriately, the limited emissions will fall automatically. And therefore, we should look at them, but we don't need to focus at them. If we focus on CO2 and we focus on reducing the CO2 by really clean technology, that will automatically reduce, or by default, reduce the limited emissions. So we evaluated a German energy system. And before giving the results, I need to say something about the methodology, how we did that. It's a cost optimization of the energy system under certain constraints. So our optimization criterion was reducing the cost to the lowest level. And the constraints were that the consumers need to get the energy at an appropriate level. So what is requested must be delivered. And secondly, that the CO2 reduction will take place at the same time. So CO2 reduction and the demand are the constraints. Energy cost optimization is the optimization target. For this, we developed a modeling suite, ETHOS. It's the Energy Transformation Optimization Simulation Suite. And we entirely rely on public data. We can include proprietary data, but not for this analysis. And it is applicable basically for any region, any continent, and any country. So we are just doing in another project now some analysis for African states as a contract to the African states. We have an hourly resolution. We have one node, and we then regionalize the whole thing to 80 nodes. And we consider renewable energy, the European power grid, buildings, districts, load profiles, demand load profiles, transportation, industry, distribution, gas distribution, and so on. So we have, except for the agriculture, we have every sector in this modeling suite considered. So how does it work? It works like communicating pipes do. So if we have a system with a certain price level, and one price level gets shifted down, all the other price levels also adjust to that because they get incompetitive. And this bar here, where the price is lower, would get higher. That means, in practice, if we have less cost for PV, for instance, we will install in our program automatically more PV. And if the wind did not decrease that much in cost, the wind power, then wind power will be less. So these are all connected. Even the demand sectors are connected under each other. And it's all hourly resolved. So if we have in winter a lot of wind, for instance, and in summer we don't, this is considered. And this is resolved by calculating the hourly prices and then adding the whole thing up. So how much do we go into the technologies? Here you can see a cloud of many technologies. And we see here that we can break it down. This area we break down, for instance, here to certain technologies like straw CHP. And that is connected to another kind of straw CHP. And that is then connected via a grid to other technologies. And all these technologies compete. So we go down into a very low level of the technologies for every household, and that is specified. We have the SOFC here in, and we have pellet boilers, and we have wood CHP in, other than straw CHP, and so on and so forth. This is all characterized by investment cost, the cost range, efficiency, CO2 emissions, the potential, how much is available of that. So there are limits. We cannot just put a lot of straw CHP in and don't have the straw, for instance. The commodities we need, the operational cost, interest rate in lifetime. We always have an interest rate of 8% in our calculations. So what are the transition requirements under which we calculate the whole thing? Basically, we have to meet the climate targets, 1.5 to 2 centigrades. And I already showed you what that means. It means pretty extreme targets. It means really negative emission beyond 2050. Germany had cast a new goal into law now. It is climate neutrality by 2045. And that includes industry, that includes all the sectors. It's been cast in law this year. After the energy transition period, the energy ideally should be no more expensive, maybe a little, but all in all, not more. Limited emissions I already commented on. I don't focus on that so much because I really believe they come by default if we don't introduce messy technologies in between, but they would also generally make CO2. And a lot will be controlled by prices. So easy technologies, electrical power directly converted, directly transmitted and used, hydrogen directly transmitted and used. These will lead to low levels of limited emissions, and we'll cut that out by default. Electricity, fuels, and heat must be available with a high reliability, and that from renewables, because we deal with renewables, and renewables are not at all reliable. So we have to think a little about storage. And what's very important to me is that heterogenic, carcinogenic, poisonous substances are to be avoided in public handling. I'm not saying they have to be totally avoided in chemical factories or so. They can be handled there. We have the knowledge and we need these substances to a certain degree, but we should not introduce them to transportation. We should not introduce them to daily life of people. And we should be careful how much we really need to transport, because whatever you transport also gets damaged to a certain degree. And we have oil spills, we have oil chemical spills. And if we rely on that for energy technology, then it's really getting bad because these are huge amounts. If we rely on such substances for chemical use in chemical factories, I think it's fully fine. They can be contained. Nuclear hazards, yes, we need to consider them. And the radiative forcing is to be considered for methane. Methane has a radiative forcing of 30. That means one molecule of methane is as bad if it slips as 30 molecules of CO2. And with that, you cannot really substitute coal by or oil by methane, because if there's a very limited slip, it already compensates for all the benefit the methane would give us. The transition pathway from 2050, we studied in the year 2019, and that's the basic study I show you. It's a little pity that this presentation here is about 6 weeks too early, because we have new results, but they are not yet published, and we will publish them by end of October. And there we investigated a 2045 climate neutrality study. And I will give you some glimpse on that. And it shows in the end that the results are pretty steady, and that we also can really talk about the 2019 study and just compare it with the 2045, the 2021 study, because the basic teachings are very similar. So going from 80% CO2 reduction to 95% CO2 reduction means that the hydrogen demand triples. So we have about 4 million tons of hydrogen in different sectors, mostly in transportation and mobility transportation, in 2050 in our study. But if we go then to a 95% scenario, we also have it in energy use and in industry, because industry needs a lot of energy, which right now is furnished by coal and by oil. So for Germany, that means we need about 4 million tons of hydrogen in the 80% scenario, and in the 95% scenario, we need about 12 million tons across all sectors, including the process heat. The climate neutrality scenario adds no further hydrogen to the demand. And that was very interesting for us. So we checked that, and the effect is that we will have cheaper renewable energy than we were supposed to have, or we were anticipating in the year 2019. So the energy prices dropped during that time, and they dropped substantially. So we now calculate with 20% less of renewable energy prices. And therefore we have other costs which increased, but this renewable energy price, which got lower, resulted in more energy production in Germany at home, which before was imported. And it was imported before because in Germany, the PV is not that effective. And for instance, in Saudi Arabia or in close to the equator, the PV is much more effective and can be transported as hydrogen into the country, to Germany. Because it was cheaper, relatively a lot was transported, 12 million tons to Germany. Now the energy got cheaper, so we would import less, but the relative demand in the climate neutral scenario increased. So relatively, we needed more. And that then exactly gave, by chance, again, 12 million tons. So we didn't trigger that. These two effects were compensating. And that was pretty interesting. But 12 million tons is a lot. And we have to take care how to generate it and how to import it. Hydrogen and methane demand. If we go for an 80% scenario, we still can emit some CO2. Therefore, we see little hydrogen, but an increase in methane demand. Once we go to the 95% scenario, we see a strong increase in hydrogen over time and a total drop close to zero in methane demand. That's pretty clear, but that also means this infrastructure, which we have as a natural gas infrastructure now, needs to be converted to hydrogen at a pretty early time between 2030, 2040. We already have basically 2022, at least for planning, it's already kind of 2022. And so they're in between of 8 to maybe 12, 13 years left. And that's not much for really doing all the planning and the conversion of this technology to hydrogen and of the installations to hydrogen. Again, if we go now for the climate neutrality, it adds hydrogen in certain sectors, it reduces it in other sectors because they can use more power. And the sector which is being reduced then is basically transportation, mobility, more power, electrical power goes in there. Therefore, industry increases and also the energy sector increases a little, and the whole bar stays the same. It's not a big shift. We notice it, but it's not a real big shift. What about the gross power production in Germany? By 2050, in a 95% scenario, which is this area here, we would need about 1,000 terawatt hours, and that's about twice as much as we need today, about twice as much, not exactly. And then we have some bioenergy. I personally questioned this a couple of times, whether it is so much what we have, but apparently we can calculate that. And we really painstakingly investigated it. So there seems to be a notable contribution of bioenergy. And then we have 220 terawatt hours of import hydrogen, which is 6 million tons. And then we have the 310 million terawatt hours, again 6 million tons of hydrogen, which we produce at home. The difference, this is the same amount of hydrogen, which has two different energy contents. And the difference is if we import hydrogen, it's just calculated as the hydrogen being imported and the heating value of the hydrogen being imported. Whereas here, we just calculate the power used, and between these two figures, that's the efficiency of the hydrogen. So we can see it is a very notable chunk which we need for the different sectors. So what about cost? If we look into cost, about 20 cents per kilowatt hour roughly can be taken by transportation, and they still stay at the same level of cost in driving as today. That's called opportunity cost. If we go all the way down to steel making, we end up at 2 cents per kilowatt hour, which is a pretty dire number because nobody has a good idea today how to deliver hydrogen for 2 cents per kilowatt hour. Though there are some opportunities by reducing the energy demand of the steel making process, so that we might climb up a little, but it's not much. We can climb up a little here, this axis, and make it a little more effective. For market introduction, and industry here is in between, buildings are in between. We might need it there, we might not, it's not sure yet. We are investigating that. Reconversion to electrical power definitely is necessary, but these prices are extremely fluctuating from €1 per kilowatt hour to a couple of cents per kilowatt hour. They're extremely fluctuating on the market. So this is hard to calculate with. For market introduction, it's very important that we have the transportation breaking the ground for the infrastructure, and the others can come up when bigger amounts of hydrogen are being needed, when electrolyzers are being tested and they are already bought down in price, so the prices got lower by quantities which have been bought. That's the same with windmills. They started very expensively. Now they are down in prices. So we need the high price areas for market introduction in order to come down and make it happen in the industrial sectors. So what are the technologies? We have electrolyzers, we have storage pipelines, big storage again, there's a small storage here. We have trucks and ships. That's basically the infrastructure we need. And the big assets will be the electrolyzers that will make it happen, that we can convert the power to hydrogen, and then transport the hydrogen via pipelines is always the cheapest solution we found. We calculated a lot of cases. It was always the pipelines which came up, particularly when they don't need to be built newly, but just can be taken and reconverted to hydrogen from natural gas. Then we need hydrogen storage, and that's a bigger question. Some countries have rock-salt caverns. That's an easy game. It's cheap. One can store the hydrogen very well in there. Some countries don't, so we need liquid hydrogen here, I think. And the liquefaction process is a very important process because we also needed to transport the stuff via ships. Nobody will transport hydrogen in the gaseous form in a ship. That's not true for a truck, though. There we have the opportunity for shorter distances to go with the 500 bar trucks, which have been developed. They're pretty cost effective. For longer distances, it's again liquid, but it can also be trains where it can be transported on, as long as the trains are not electrified, the train rails. There's a little caveat about having hydrogen under a power line. But otherwise, we can see that liquid hydrogen in big quantity trade in the end will have a notable share, because we will do that partially via pipelines, but partially via ships. So hydrogen as a commodity, I'm talking here of millions of tons of hydrogen, and we have to put the question, can we do that? Is it reasonable? I'm sorry for the shift here in the graphs. Is it reasonable to do that? And we can see, for instance, in Morocco, we can produce about 2.5 million tons per year, maybe a little less, a little more, but 2.5 million tons is a pretty reasonable figure for Morocco. Then we have the potential in Algeria. That's already better. There we are about 90 million tons, 88 million tons, a little short of 90 million tons. In Saudi Arabia, it's again over 100 million tons. And here we have to say, as well as in Algeria, we only took for our calculations 5% of the very best locations. And 5% of the very best locations gave these numbers. So it's a very reasonable number that we can produce it. So with these two countries here, only from solar power, we could already furnish roughly 200 million tons, and we need 6 million tons as an import for Germany, and that will be maybe similar for other countries, whether they need 50% or 70% or whatever they need as an import, but it will not be 100%, and therefore we are far, far away with the potential, and even with the economic potential from what we really need. And insofar, it can definitely be furnished already from solar. Now let's have a look into wind. Here we have a potential of about 120 million tons per annum from Patagonia. Iceland has a potential of roughly 10 million tons. Canada, 130 million tons. So we can close this chapter and just say, it's feasible, it will work. Same, by the way, for Europe. We didn't check that for Asia, but for Europe, where we can say the countries can produce a lot of hydrogen themselves. There are some countries which are landlocked, like Switzerland. That's a little difficult. But if you look into France, for instance, which has a coastline, they can produce 10 million tons per annum for less than €3. So, and that holds true for a lot of countries. Germany can make 1 million tons for less than 3, and you see 10 million tons for less than 4. euros per kilogram. We allocated that, and we came up with an allocation scheme which is much more regional. We don't think it is very realistic that from Australia, for instance, it will be shipped all the way around Africa to Europe, but the shorter transportation routes will apply because the transportation of hydrogen is more demanding than the transportation of oil, and it's more costly. So I already said something about market introduction, and I again would like to say also these chains, these change of the economy have to be developed from the high price markets to the low price markets. Otherwise, I don't see how we can really, out of nothing, feed steel making with hydrogen of 2 cents per kilowatt hour. The cost of transition. So we made the first calculation was 95% CO2 reduction. I don't look into the 80 anymore here. For 1,800 billions, which have to be paid for over 30 years. And that results into 60 billion. 1,800 is an unimaginable sum, but 60 is not so unimaginable. And if we consider the 30 billion we have to put into the damages, just for one big damage we had in Germany of the flood, it's just twice it. So we can pay for it. It's not nothing, but it also opens up new economic opportunities, which are not totally not considered here. So then we recalculated this scenario, which we did in 2019. We recalculated it in 2021 with the new cost, and we called it the business as usual scenario 95, whereas business as usual is this one here, not the IEA business as usual. So we came up with minus 20% cost compared to that one on the renewable side and on the electrolyzer side and so on and so forth. So it's an average number. The climate neutral scenario, though, needs 52% more cost based on the numbers here. And 20% we already are lower than here. So we compare with 32% increase. So if we take our old figure from 2019, we add 32% to that. And we would end up with about less than 90 billion for Germany. And that still seems very affordable. So when we compare the cost scenarios, again, the 80% was defined as 100% baseline. Then 95% CO2 cutout adds 180% to the cost compared to the 80% scenario. The interesting thing is that taking it 5 years earlier to 2045 and then make it totally climate neutral, adds only 30% to the cost of 50% on the 2019 level. In total, because we got cheaper, only 30%. So this shows that the whole climate neutrality scenario, which looked very, very demanding, and I personally expected it to be much more costly, comes down in cost to a very reasonable sum. And we can say we can afford it, and I personally would say we must afford it, seeing these high expenditures we have now, which is not only the German flood, it's also Ida, And in the US already, they are talking about the competition of mitigation and adaptation money. And that's a big menace we have for the future. If the adaptation money competes with the mitigation money, then we might run into a problem. So with cheaper renewables, less hydrogen is needed for direct use of electricity. That I explained. With more ambitious climate goals, more hydrogen is needed, but relatively more hydrogen. So the absolute hydrogen amount, because of this effect, is very limited. The reassignment of gas pipeline is cost effective, and both level off in our scenarios about 200 terawatt hours of hydrogen corresponding to 12 million tons of hydrogen. On the market, substantial amounts go to industry. The opportunity costs of the hydrogen are lower than the market introduction prices. The transportation provides high opportunity costs for hydrogen, and that is to be used as an opportunity to introduce hydrogen in the societies and to make it spread through the society where the opportunity costs are too low to really introduce it in the first place. Then with households, we have some open questions which we are just investigating. It's a question how many renewables can really be installed. Can houses really be refurbished? What we checked in the Institute is we can say a house can be refurbished by its building standards. But we did not check yet whether we will be in a position to really provide all the craftsmen in that time, to really gear up the industry to refurbish all the houses at that time, or do we need additional mechanisms to flatten that curve and to bring hydrogen, for instance, via the gas distribution net for some time, or even in the long run to these houses. And we now caring about these houses which are restricted under monument protection because they cannot not be refurbished. Some will be done on the legal side, but some needs also be done on the engineering side. Thank you very much for your attention. This was my contribution. And this is the team of the IEK-3, which produced these results. I have to apologize a little. It's as of pre-corona time, so the actual photo is not available. And I can tell you about 50% of these people already left the Institute, but still their legacy also contributed a lot here. Thank you very much.